Welcome to Senior High School Math Series. This time, let us have trigonometry under PreCalculus, and let us discuss about proving trigonometric identities. In a video lesson, we introduced the fundamental trigonometric identities. We had the reciprocal relations, quotient relations, and Pythagorean relations. If you haven't seen it, the link is on the description of this video. This time, let us have a recall of important concepts useful in proving trigonometric identities. Factoring, simplifying expressions, and working with fractions are some of the algebraic procedures commonly used in proving trigonometric identities. Let us recall some of these procedures. Factor and simplify. Cosine cube A plus cosine A sine squared A. In simplifying and factoring expressions involving trigonometric functions, we follow the same rules in factoring algebraic expression. So in here, cosine A is a common factor, hence we factor cosine A times the quantity cosine squared A plus sine squared A. From the Pythagorean relations, we know that cosine squared an angle plus sine squared the same angle, that is equal to 1. Hence, the simplified form is cosine A. Next, combine the two terms 1 plus sine A over cosine A. We are combining a whole number and a rational expression in the form sine A over cosine A. So we have the LCD as cosine A, then cosine A divided by 1 times 1, that is cosine A plus sine A. Next, we have factor sine squared A plus sine squared A cosine squared A. Again, sine squared A is a common factor, so we have sine squared A times the quantity 1 plus cosine squared A. Another one, we have 2 sine squared A plus sine A minus 1. So we can factor this in the same way that we factor a quadratic expression. So we have product of two binomials, 2 sine A as the first term of the first binomial, and sine A as the first term of the second binomial. Negative 1 is negative 1 times positive 1. Since the middle term is sine A, then the outer terms whose product is 2 sine A must be positive. So we have sine A plus 1, and the other one 2 sine A minus 1. Next, let us have operations involving trigonometric functions. So we have cosine B plus sine squared B over cosine B. Again, the LCD is cosine B. Then we have cosine B times cosine B, that is cosine squared B, plus sine squared B. From the Pythagorean relation, cosine squared B plus sine squared B is equal to 1. Therefore, final answer is 1 over cosine B. Another one, we have cosine A over 1 plus sine A minus cosine A. So the LCD is 1 plus sine A. Then we have cosine A minus cosine A times the binomial 1 plus sine A. Distributing cosine A to the terms inside the parentheses, we have cosine A minus cosine A times 1 minus cosine A sine A. And this is over 1 plus sine A. Cosine A minus cosine A is 0. Therefore, we have negative cosine A sine A over 1 plus sine A. This time, let us proceed to proving trigonometric identities. One way to prove that an equation is an identity involves transforming the more complicated side into the simpler side. Work on one side only. Also, we use the fundamental identities in transforming the more complicated side of the identity into a simpler expression. Let us have example number 1. Prove cotangent theta secant theta is equal to cosecant theta. From the previous slide, in here we can say that the left-hand side is the one that is more complicated. So, working on the left-hand side, we have cotangent theta secant theta. We're going to manipulate this left-hand side in such a way that we can simplify this into an expression or a trigonometric function that is equal to cosecant theta. We know that cotangent theta from the quotient relation is equal to cosecant theta over secant theta. And this expression for cotangent theta is multiplied by secant theta. We have secant theta over secant theta, that is equal to 1. Therefore, we have cosecant theta and the identity is now proven. Let us have another example. Prove 1 minus sine b over cosine b is equal to cosine b over 1 plus sine b. From the first slide, we are told to choose which one is more complicated and express it into an expression that is the same as the simpler form of the identity. However, in this identity, we have two sides that appears to be simple. So in order to prove this identity, we're going to use algebraic manipulation. We're going to use algebraic manipulation in such a way that we are going to multiply one of these expression by 1. However, we're going to express 1 in another form. Let us work on the left-hand side. In this form of a trigonometric identity, you can choose either the left-hand side or the right-hand side. So, working on the left-hand side, that is 1 minus sine b over cosine b. Multiplying this expression by 1, 1 minus sine b over cosine b times 1, we're going to write 1 in another form, and that is the conjugate of 1 minus sine b. So we have 1 plus sine b over 1 plus sine b. It is the same way as multiplying the expression by 1, using the conjugate of the numerator. Let us proceed in multiplying. In the numerator, we have 1 minus sine b times 1 plus sine b. This is the product of difference and sum. So the result is the difference of two squares. Then we have 1 minus sine squared b. And in the denominator, we have cosine b times the quantity 1 plus sine b. Take note that we are manipulating the left-hand side until we reach an expression that is the same as the right-hand side. In the resulting expression, the numerator is equal to cosine squared b, that is using the Pythagorean relation. So we have cosine squared b over cosine b times 1 plus sine b. From this resulting expression, we can cancel cosine b because cosine squared b over cosine b is equal to cosine b. Hence, we have an expression that is the same as the right-hand side, that is cosine b over 1 plus sine b. The identity is now proven. Let us have another example. Example number 3. Prove the identity sine cube A plus cosine cube A over sine A plus cosine A equals 1 minus sine A cosine A. So in here, the left-hand side is the one that appears to be more complicated than the right-hand side. We're going to work on the left-hand side, and that is sine cube A plus cosine cube A over sine A plus cosine A. Another way to prove trigonometric identities is using factoring. Notice that the numerator of this expression is of the form sum of two cubes. Factoring the numerator, we have sine A plus cosine A times the quantity sine squared A minus sine A cosine A plus cosine squared A using the formula for factoring sum of two cubes. In the denominator, we still have sine A plus cosine A. Notice that sine A plus cosine A is a factor in the numerator, and it is also a factor in the denominator, so we can cancel. Sine A plus cosine A over sine A plus cosine A is equal to 1. And rearranging the remaining factor in the numerator, that is sine squared A plus cosine squared A minus sine A cosine A. By Pythagorean relation, sine squared A plus cosine squared A is equal to 1. Hence, we have now an expression that is equal to that expression in the right-hand side of the original identity. 1 minus sine A cosine A. Let us have example number 4. Prove sine B plus cosine B is equal to secant B plus cosecant B over tangent B plus cotangent B. So in here, the more complicated side is the right-hand side. Therefore, we're going to work on the right-hand side. Another way to prove trigonometric identities is to express other trigonometric functions in the form of sine and cosine functions. Therefore, working on the right-hand side, that is secant B plus cosecant B over tangent B plus cotangent B, we're going to express each of these trigonometric functions in the form of sine and cosine function. Secant B is 1 over cosine B. Cosecant B is 1 over sine B, that is in the numerator. In the denominator, tangent B is sine B over cosine B using the quotient relation. Also, cotangent B is cosine B over sine B. Now, what we're going to do is to combine the terms in the numerator and the denominator separately. In the numerator, the LCD is cosine B sine B, and then we will have sine B plus cosine B in the numerator. In the denominator, we have cosine B sine B also as the LCD, and then the numerator will be sine squared B plus cosine squared B using the techniques in adding fractions. From Pythagorean relations, sine squared B plus cosine squared B is equal to 1. Then what we have now is a quotient of two fractions. To do that, we copy the fraction in the numerator, that is sine B plus cosine B over cosine B sine B, and multiply this by the reciprocal of the fraction in the denominator, that is cosine B sine B over 1. Now, cosine B sine B over cosine B sine B is equal to 1 also. Therefore, the right-hand side is now simplified as an expression that is equal to the left-hand side, sine B plus cosine B. Hence, the identity is proven. Let us have one more example. Example number 5. Prove tangent A minus sine A over sine squared A is equal to tangent A over 1 plus cosine A. Let us work on the right-hand side and let us manipulate tangent A over 1 plus cosine A in such a way that we reach our goal, which is equal to the left-hand side, tangent A minus sine A over sine squared A. So what we're going to do here is to multiply both the numerator of tangent A over 1 plus cosine A and the denominator by the conjugate of the denominator, that is 1 minus cosine A. And that is the same as multiplying the expression by 1. In the numerator, we have tangent A minus tangent A cosine A. In the denominator, we have product of sum and difference. So we have the difference of two squares as a product. Therefore, we have 1 minus cosine squared A. Tangent A cosine A in the second term in the numerator can be simplified. We have tangent A minus tangent A is sine A over cosine A, and this is multiplied by cosine A. Let us copy the denominator, that is 1 minus cosine squared A. Now in here, cosine A over cosine A, that is equal to 1. Hence, we have tangent A minus sine A, and in the denominator 1 minus cosine squared A can be expressed as sine squared A using the Pythagorean relation, and that is the same as the left-hand side of the original identity. Therefore, the identity is proven. That will be all. Thank you for watching. Please subscribe for more math lessons.